Hello guys, welcome back to my channel. I'm Sneha S from Department of Cybersecurity from Sri Venkateshwara College of Engineering. I'm studying in third sem of Kavach. Today I'll be dealing with the topic of application of linear differentiation equation of LC circuits, which is from mathematics. Let us begin with. We'll be seeing LC circuits, linear differential equation of LC circuits, their applications and the conclusion. So this is a diagram of LC circuit. What is LC circuit? LC circuit is a combination of an inductor and a capacitor. Inductor is denoted by L and capacitor is denoted by C. Now let us see what is LC circuit. LC circuit is an inductor capacitor circuit, which I already told you. They are also called as tank circuits. They are electronic circuits that involve the use of inductors and capacitors to generate or store oscillating electrical energy. These circuits are commonly used in various electronic devices like radios, tuners, and oscillators. We can use this inductor and capacitor separately, but their combined effect gives us unique properties, that is resonant system. That's the reason we are combining them. Now let us see the linear differentiation equation of an LC circuit. It is given by Kirchhoff's law, which states that whenever a current is entering a circuit, it will be equal to the sum of the current that is leaving the circuit. And the second law of Kirchhoff is that the sum of voltage, that is potential difference, is always equal to 0. Here is an equation of the LC circuit, which is L into di by dt plus q by c is equal to 0, where di by dt is rate of change of current with respect to time, and I is equal to dq by dt, which is rate of change of charge with respect to time. So this gives L into d square q by dt square plus q by c is equal to 0. This is the equation. Now let us see the main topic of our today's session, that is application of linear differentiation of LC circuits. Why are we even discussing about the application of linear differentiation of LC circuits? Because we have to analyze and understand the dynamic response of the circuit over time. Let me first brief you that these LC circuits depend on only two quantities, that is the current and the voltage. So the first one is transient response analysis. This can be seen in switching circuits. Like if you on or off an switch, it will enter to a phase that is called a transient response. This response is given by a linear differentiation equation. It helps us to predict how the current and the voltage change over time during the transient period. So here is a circuit diagram. It has a potential difference, a current flowing through the switch. If the switch is open, it's 0, and if the switch is closed, it's 1. And we can also find a lamp here. We will be using this linear equation here in order to analyze this LC circuit. The second one is an oscillator circuit. Oscillator means oscillating current. We can see this in LC tank circuits such as radio frequency oscillators. Here this linear differential equation will help us to analyze the steady state behavior and predict the frequency of oscillation. So here we have one RC oscillator where 3 capacitors and 6 resistors are connected to each other, and 4 capacitors. And the next one is filter design. In filter design, there are band pass and band stop filters, which are often used in filter design. The linear differential equation helps us in understanding the frequency response of the filter, and it helps us to design circuits that allow and block frequency ranges. So if there is a particular band, then the signal will be flowing, and if there is like cutoff frequency or if there is any threshold values, then the frequency will not be allowing that. The next one is tuning circuits. Tuning circuits are used in radio frequency applications. They are basically used to tune the frequencies. It helps us to analyze resonance phenomena, enabling engineers to design circuits for optimal tuning. Here is a circuit diagram of your tuning circuit. The next one is transmission lines, which we can see in local area networks. Transmission lines helps us to analyze impedance matching networks. It helps to understand the impedance characteristics of the circuit, aiding the proper matching of impedances for efficient signal transmission. The next one is RF amplifier. Amplifier regulates the flow of current. It is basically used in radio frequency applications. Here is a diagram of an RF amplifier. The next one is signal processing. Signal processing deals with signal filters. Here will be filtering signals using LC circuits. It helps us to analyze the response of the filter to different input signals. The first one is low pass filter. The second one is high pass filter. The third one is band pass filter. And the fourth one is notch filter. We have different graphs given here, wherein we see in low pass filter and high pass filter, the signal is blocked. And in the band pass filter, there is a band which allow the signals to flow. And in the notch, you can see a narrow groove type frequency. And the eighth one is energy storage and transfer. Energy storage systems. Here the energy is stored and transferred between inductor and capacitor in the circuit. We can find applications in renewable energy, factories, offices, business facilities, homes, transmission and distribution. And the final application of LC circuit is feedback loops. These are helped in building or designing stable and responsive control systems. Let us summarize whatever we have studied. So the first thing we studied is the LC circuit, which is combination of an inductor and a capacitor. And it mainly depends on two more quantities, that is current and the voltage. It is a powerful tool in the analysis and design of various electronic systems and applications, which provides insights into the time-dependent behavior of currents and voltages in various circuits. Thank you, guys.